In this lecture, we'll talk about interpolation and in particular polynomial interpolation. In polynomial interpolation, we start with a set of points xi, yi, where I goes from 0 to n. And we try to fit a polynomial through these points. That means y equals j equals 0 to n aj x to the power j. The idea here is that the polynomial must pass through all the above points exactly, which means that yi must be equal to sum of aj xi to the power j for j going to 0 to n. Now let us see how we can accomplish that. The fundamental question of interpolation is that given a set of discrete points xi, yi, our goal is to fit a curve, usually a smooth one, exactly through all the points, which means that let's say these red dots are my points xi, yi, and when I fit a curve like this blue curve, it should pass exactly through all the points. The equation of this curve could be anything, but in particular we look for polynomial interpolation, primarily because the polynomial has this property that they are differentiable up to any order. So the problem of polynomial interpolation is that given n plus 1 discrete points xi, yi, such that each of these xi are distinct, which means xi not equal to xj for I not equal to j. And our goal is to fit an nth degree polynomial, that is Pnx, which is given by a0 plus a1 x plus a2 x square all the way up to an xn through all the points. Now to generate this polynomial y equals Pnx, we must know these constants a0, a1, a2, etc. up to an. So which means that I have this n plus 1 constants, and I know that this polynomial will pass through this n plus 1 points xi, yi exactly, which means that I can write a0 plus a1 x0 plus a2 x0 square up to an x0 n equals y0. And similarly, the polynomial will be satisfied by all other points up to a0 a1 xn plus a2 xn square up to an xn to the power n equals yn. So in matrix form, I can write this as a coefficient matrix, which is 1 x0 x0 square up to x0 n, and the last row is 1 xn xn square up to xn to the power n multiplied by the unknown column vector a0 a1 up to an, and on the right hand side I have this column vector y0 y1 up to yn. And since I know all the points xi, yi, we can see that we know the coefficient matrix here, and also we know the column vector on the right hand side. Therefore, we should be able to find the unknown a0, a1, an, etc. And we can clearly see that even though the polynomial is nonlinear, all we have to do is to solve a system of linear equation to get the unknown a's. But before we do so, at least we have to find that this matrix, coefficient matrix, is invertible, or this x equal to b does have a solution, or probably has an unique solution. So let us first check that. This coefficient matrix here has a particular structure. This is a famous matrix known as Vandermonde matrix. In Vandermonde matrix, we have this structure of 1 x0 x0 square up to x0 n, and the last row is 1 xn square up to xn to the power n. When you have this sort of structure in a matrix, with little bit of effort, you should be able to find the determinant of this matrix. If you find it, you will see that the determinant will be the product of xj minus xi, and this will be a non-zero number if xi and xj are different for all xi and xj, and that is an assumption we have taken initially, which means if xi and xj are unequal, then this determinant is non-zero. And if the determinant is non-zero, which means that V is a non-singular matrix and V inverse actually does exist. If V inverse exists, then we can solve this problem of finding this A0, A1, An column vector by writing this column vectors equals V inverse multiplied by this column vectors y0, y1, etc. Since V inverse exists, we have an unique solution of A1, A0, A1, A2, etc. So AI will be unique. Now for this nth degree polynomial y equal to A0 plus A1x plus A2 up to An xn, if all these A's are unique, we can say that the polynomial is unique. However, if you actually try to solve this set of equation, you have to of course solve invert this van der Waals matrix, which may not be easy, but also this van der Waals matrix is not a very good matrix. It is, in linear algebra terminology, this is not always well conditioned matrix, or you can see there are some apparent problems in this matrix. For example, if xj and xi are close to each other, then the determinant will be small and the matrix will go very close to a singular matrix. In such a case, the matrix will behave in a very unstable manner, which means that a small noise in the matrix element will bring a large noise in V inverse, which means that my calculation of AI could be off to a great extent. So how can we avoid such situation? We can avoid such situation by introducing a new idea that is known as interpolating polynomials. And if we use this idea as interpolating polynomials, which are some sort of special kind of polynomials, you will see that we will completely avoid using this van der Waals matrix. And in upcoming lecture, we will see that what are these interpolating polynomials and how we can utilize them for polynomial interpolation. For now, you can solve this small exercise where you have a set of data xi, yi for I going to 0 to 4, and you take this data, try to fit a polynomial that will pass exactly through all these 5 points, and you invert a van der Waals matrix to get this polynomial. You already have the computer programs of Gaussian elimination or similar techniques. You can use these programs to get the polynomial. So that's all for this lecture. Thank you, and I'll see you in next class.